Very good evening to everyone. My name is Pankaj Bharmoria, and I hope you're listening to me clearly actually. So I'm a researcher at University of Göteborg, Sweden. And today I'll talk about my research on photonics bioplastic films for triplet sensitized wideband photon harvesting. So many of you must be chemists actually. So you might have studied in photochemistry that the photoemissive organic or quantum dot, they exist in two photoemissive states. One is singlet state and the another one is triplet state. The triplet state is actually different from the singlet state based on its the spin of its excited electron. You can see over here. This spin is parallel related to the ground state. Because of that, it has a spin angular quantum number of 1 and overall spin multiplicity of 3. That is why it is a triplet state. But it is a polyspin forbidden state and it is difficult to populate at room temperature. And in most of the organic molecule, it exists as a non-emissive dark state. However, in some of the molecules like porphyrin, phthalocyanins, because of the high singlet to triplet transition, these molecules, they show photoemissive triplet state at a room temperature. This is due to the high spin orbit coupling in these molecules that results in transition of the singlet state to the triplet state. So the idea of my research is to use this active triplet state of the photoemissive triplet molecule to sensitize the triplets of the non-phosphorescent organic molecule to harvest their triplet energy. And we are doing it using a photophysical process known as photon upconversion. So photon upconversion is actually a process where we excite the molecule at low energy and it shows the emission at high energy. That is why it is photon upconversion, because it is upconverting the low energy into the high energy. And the upconversion process that we are using is triplet annihilation based molecular photon upconversion. So what is that? Actually, in a TTUC system, it is actually an ensemble of chromophore comprising of triplet sensitizer and triplet acceptor. The triplet acceptor is actually the one which has non-emissive triplet state, whereas the triplet sensitizer or the donor is the one which has a emissive triplet state. What happens is that we excite the triplet sensitizer at low energy, okay, and while going back to the ground state, it transfers its triplet energy to the dark triplets of the acceptor or annihilator molecules. And when two such sensitized triplets of the acceptor, they meet in the space-time, they undergo triplet annihilation that results in the formation of a high energy singlet state that shows the anti-Stokes delayed fluorescence known as the upconverted fluorescence. So in TDOC, so you can see that we sensitize the two sensitizer molecules actually, or we excite the two sensitizer molecule, and that results in the formation of a one acceptor photon emission actually. So that is why you can see over here that two photons they are combining to form, or two low energy photons they are combining to form one high energy photon. This is the energy diagram of TTUC. You can see clearly over here that when we excite the donor, it goes to the high energy singlet state, then by intersystem crossing to the triplet state. And while going back to the ground state, it transfers its triplet energy to the acceptor. And when two such sensitized acceptor molecules they meet in the space-time, they undergo triplet annihilation, which form the high energy singlet state of the acceptor molecule, which finally shows the fluorescence emission or anti-Stokes delayed fluorescence emission. But for the TTUC to happen, the molecule should remain within the distance of less than 1 nanometer, because the energy transfer in TTUC that occurs via electron exchange mechanism. So the wave function of the two molecules, they should overlap with each other for the perfect electron transfer. So the energy transfer or the occurs in this system via Dexter energy transfer mechanism. But why we are studying this system? Because they do have certain application. One is in biology and the another one is in the solar cells. How? Actually, the conventional solar cell that we see around us, they have a limit of converting solar energy into the electricity. And that limit is known as Shockley-Queisser limit, and it is at 33%. Okay. So the solar cell that we see around us, they can convert only 33% of the solar photon that fall on them into electricity. But why? This is because of the fact that solar cells, they function at a particular band gap actually. And if you put energy higher than that of their band gap, that is lost in the form of thermal energy. And if you put energy on them which is lower than that of their band gap, that is lost in the form of transmission actually. So what photon upconversion material can do is they can they can they can avoid the transmission losses by upconverting the transmitted subband gap photons of the solar cell to the band gap responsive light of the solar cell to increase their solar energy conversion efficiency. But for the practical integration with the solar cell, this TTOC system, they must be prepared efficiently in the solid state, which is a major challenge. And what these challenges are, because in the TTOC system, we use organic chromophores, okay, which are polyaromatic hydrocarbons. And these molecules, they have a tendency of aggregation in the high concentration. And for the TTOC to happen, we need them in high concentration in the soluble form. Because if they will aggregate, then the electron wave function, although they will actually overlap with each other, but before that, there would be concentration quenching of the fluorescence. And because of that, the upconversion efficiency will decrease. And since we are thinking of translating them into the solid state, in the solid state, this system or this problem get worsened, because in the solid state there would be no solution actually for the molecule to separate, and they further undergo this aggregation in the solid state. So these are two challenges in the what should I say, in the solution or in the solid state. The another major challenge is because we are dealing with a triplet state. So the molecular oxygen that we breathe, that exists in the form of triplet state in its ground state. So for example, if you want to achieve the TDOC in the solution state, in the presence of oxygen, it will never happen, because molecular oxygen will always quench the triplet state of the organic chromophore, and the same will happen in the solid state. So molecular oxygen is also a major challenge actually. So we always need to prepare system which are deoxygenated or in the absence of air. That adds, that add additional cost to the overall economy of the process. So we need to develop system which should function in the presence of air and which should be efficient as well. Okay. So my research is actually focused on overcoming these challenges using a soft material approach of protein surfactant chromophore co-assembly. Okay. And using this approach, I have developed photon upconversion bioplastics, which function efficiently in the solid state, which I'll present you in the following slides. So the idea of photon harvesting in soft material, because when I went for my first postdoc to Japan, actually, I started working on this photon upconversion process. So the first challenge that I received was to prepare efficiently air-stable aqueous TTUC materials. Actually, in my PhD, I have worked extensively on the surfactant protein system. So I knew from that that these surfactant molecules, they form complexes upon interaction with the protein at a certain high concentration. Okay, so I thought of the idea, if I increase the concentration of both surfactant and the protein, then I will be able to develop a condensed system where the surfactant, they will form hydrophobic reservoir inside the protein. And because of its thick fiber network of various protein at high concentration, they can prevent the oxygen inflow into the chromophore region. So by using this approach, I can solubilize the chromophore in the hydrophobic domains of the surfactant, and then the protein that can act as an oxygen barrier. So I worked on this process, and we could develop the first chance photon upconversion hydrogels actually, which showed nice or very stable photon upconversion in the presence of air. You can see over here, when this system is actually excited at 532 nanometer, it is showing emission at 437, or blue emission actually, which is the energy upconversion. Later on, I thought of the idea that what if I dry this hydrogel in the air. So I found out that when all of the water that goes away due to evaporation, this hydrogel transforms into a very nice bioplastic film. And when I checked the upconversion property of this system by exciting with 532 nanometer laser, it showed very nice blue emission. This was quite surprising because generally what happens is that when you go from solution state to the solid state, the concentration quenching occurs, but it didn't happen in this particular case. But why? The reason for this one was when we evaporated the water, since we use liquid surfactant to form co-assembly in the water system, okay, which has a high boiling point, after evaporation of the water, this surfactant liquid that didn't evaporate. Instead, it formed isolated surfactant droplets inside the protein film. And in those isolated droplets, it also dispersed the chromophores very nicely, just like the one in the solution state or in the, just like the one in the solution state. So these were the components actually. I used diphenanthracene sulfonate as an annihilator and platinum octacyl porphyrin as a sensitizer, and Titan X100 as a liquid surfactant and gelatin as a protein. So when I casted this solution and evaporated the water, it resulted in the formation of a nice film. And this is the structure of the film. You can see that the isolated droplets of the Titan X100 containing chromophores, they are actually acting as a reservoir for the chromophore dispersion. Moreover, the thick fiber network of the gelatin or the protein that is preventing the oxygen inflow into the chromophore region. To further elucidate this structure and the mechanism, we did various characterization. But this is a cross-section SEM image of the film. You can see the liquid droplets of this surfactant liquid clearly dispersed nicely inside the protein fibers. We also did this differential scanning calorimetry analysis, and you can see over here, this is the heating cycle of the film, and we could observe peak for the Titan X100 liquid inside the protein film. This shows the fact that TX100 is present in the form of liquid inside the protein film. From the dark field polarized microscopic imaging, we could see that this film is semi-crystalline. This is due to the fact that gelatin itself is a semi-crystalline, and it comprises of this crystalline and amorphous domains. So we thought of the fact that probably the surfactant got dispersed in the amorphous domains, and the crystalline domains of the gelatin fiber that protected or that avoided the oxygen inflow into the chromophore region. We further confirmed it from the powder X-ray diffraction. You can see this is the peak due to the crystalline nature of the gelatin, and this is the peak due to the amorphous region. So this film is actually a semi-crystalline film. You can see this is a steady state upconversion emission spectra of the film in the air. So this film is showing very nice photon upconversion in the air, which indicates that there is no oxygen quenching and TTUC can work efficiently inside this film. From this figure, you can see that this is the phosphorescence of the donor. So it is decreasing, and this is the fluorescence of the annihilator or emitter actually. So it is increasing. It is indicating efficient triplet energy transfer from the sensitizer or donor to the acceptor molecule. And then we further measured other upconversion properties like threshold excitation intensity and the upconversion efficiency. And this film worked very nicely near the subsolar irradiance, which increases its significance for the practical applications. Moreover, this film showed very high upconversion efficiency, which is 15.6% in the solid state, which is equivalent to the record value in the solid state. And even after 2 years of storage at room temperature, only half of the upconversion efficiency that got decreased. So it is showing a very nice durability as well, and which is a record till date actually. But why? And how oxygen is protecting the triplets actually. So for that, we did one observatory experiment, which is a triplet lifetime. So long triplet lifetime shows that the triplets of the molecules, they're very much stable against oxygen. But why? So for that, we did a counter experiment of TTUC in a Titan X100 solution in the air and one in the film. You can see over here that the upconversion emission that decreased with the passage of the time in the Titan X100 liquid in the air However, in the film, it remains stable. So additional component in the film is only gelatin, which shows the fact that gelatin is actually protecting the triplets from quenching by molecule oxygen. Then we did thermomechanical analysis of the film because it is very, very important if you want to consider them for the practical application, actually, for the integration with the solar cells. And we found that these films are mechanically very, very stable from the storage modulus data. And then we did thermomechanical reversibility of the up conversion experiment by heating the film up to 65 degrees Celsius and then cooling to 20 degrees Celsius. And we found out that although the up conversion decreased at high temperature, but while coming back to the room temperature, all of its up conversion property that got reversed, which shows that although at a high temperature, you can see a decrease in the up conversion, but when the film will come back to the room temperature, actually, it will acquire all of its original up conversion properties, which make it stable for the practical applications. So this was the work which I did at Kyushu University, and half of the work I did at Chalmers University of Technology, Sweden. So based on these results, actually, I wrote a grant for the Marie Curie for NR light harvesting in artificial protein lipid chromophore co-assembled molecule system, and luckily I got the grant. And then I started working on NI to blue or red to blue photon up conversion bioplastics, because for practical integration with the solar cell, we need to harvest the NR light or the far red light. And during my tenure at Chalmers, I could prepare the red to blue TTUC bioplastic film. I'm not showing the compounds right here because this paper is under review at the moment, but you can see the results that this film shows very nice blue up conversion emission upon excitation with the 633 nanometer red light. Moreover, it showed a significantly low threshold excitation intensity of 95 milliwatts centimeter inverse, which is equivalent to 95 suns, and record up conversion quantum yield of 8.5%, the solid state till date for red to blue photon up conversion. We further extended this idea for harvesting the NR light and prepared NR to blue TTUC bioplastics. You can see on excitation with 730 nanometer far red NR light, it is showing very nice blue up conversion emission. Nowadays, one of the key problem for the technological development is what will happen to the material that we are preparing now, whether they are recyclable or not actually. So considering these things in mind, okay, we developed a post-utility recycling process for film as well. For that, what we did is we used the used film and then we cut it back into pieces and dissolved it in water. It formed hydrogel, and we developed cloud point extraction process actually. What happened is that the surfactant that we are using, Titan X100, it has a cloud point actually. So below the cloud point, it remains mixed with the solid state, but above the cloud point, it phase separates from the solid. So as it phase separated from the solid, it also take with it the harmful chromophore or the toxic chromophore that we are using. So you can see it forms a biphase at 65 degrees Celsius. So we can decant the Titan X100 and the dyes, okay, and then we can discard the biopolymer because it's just gelatin actually. So it can biodegrade in the atmosphere. But more importantly, we can decant or take out the toxic Titan X100 liquid and also the chromophore, and we can reuse them by using a fresh gelatin. So in this way, we can recycle this process and we can avoid their leaching into the environment. So using the principle of circular economy, we could recover up to 67% of the annihilator and 66% of the sensitizer molecule. And when we reuse them for the refabrication into the bioplastic films, they showed this film showed very nice photon up conversion emission. So in this process, we could develop a renewable energy capital and also minimize the waste, which are the two basic principles of the circular economy, circular bioeconomy. So this is a summary of my talk. So we developed this chromophore surfactant protein co-assembly approach, first to prepare the hydrogel, photon up conversion hydrogel, and then the photon up conversion bioplastics. These bioplastics are very, very sustainable because we can recycle them, and they show wide band photon harvesting ability. And finally, I would like to acknowledge the funders and the lab colleagues and supervisor, funders for funding me for this research, and lab colleagues and the supervisor for their assistance during the research. Finally, I would like to thank the organizer of this conference and all the listeners who are listening to me patiently. And obrigado. And finally, I'm open to answer any question related to this talk. Thank you very much for your kind attention.
Yeah, thank you for your beautiful presentation. If anyone wants, he or she can ask questions.
I think Dr. Bimbad asked some want to ask some question? Yes, please.
Can I?
Hey.
Dear Dr. Bharmoria, thank you very much for your presentation. I think it's absolutely fascinating.
Thank you.
To combine biomolecule surfactants to reduce the excess of oxygen. I was just pretty surprised by your DMA experiments on the gelatin-based materials. You got a modulus of close to 2 gigapascals or something like that.
Yeah.
Could you explain how you get such high values for gelatin-based materials? Was it in the dry state?
Yeah, it was in the dry state actually.
Okay, and no additional cross-linking?
No, nothing.
And so it's the raw material containing the gelatin and the Triton surfactant and your photoactive molecules. Does the modulus change when you add the surfactant, or is the surfactant reducing the modulus?
Yeah, you can see that. Yeah, the first one is actually for the pure gelatin film.
Yeah.
And the second one is for the this surfactant actually, because when you're doping surfactant, surfactant into the film, so surfactant remains in the liquid form actually. So definitely,
there is an additional point at this very interesting point anyway.
Yeah.
Can you explain that gelatin contributes to the reduction of the oxygen permeability inside of the material? Because usually when you have the gelatin gels I am used to work with have porosities of the round, it's 10% weight.
Yeah.
Gelatin. So we have porosities which are close to a few micrometers when you look by scanning electron microscope.
Yes.
How can such a material reduce the permeability of oxygen inside of the material?
Yeah, but actually, if you increase the concentration of the gelatin, for example, in this particular case, I use 20% of gelatin. Okay, then those fibers get thicker and thicker and thicker.
But that's not so much.
Yeah, so that increases the oxygen, that reduces the oxygen permeability. Moreover, the surfactant that we are using over here, it's a viscous surfactant. So even in its, because of its high viscosity, it's an additional parameter actually which can reduce the oxygen inflow into the chromophore region. Okay, so these two properties combined together actually they act very nicely. For example, if you increase the temperature, so at high temperature we observed a decrease in the upconversion efficiency. That was probably due to the fact that oxygen was penetrating into this region. But surprisingly, what happened was that when we decrease the temperature to, for example, room temperature, the film obtained its perfect upconversion efficiency actually. So maybe at high temperature, the reason for decrease in efficiency could not be the oxygen inflow, because what happened is that suppose if oxygen enter into this region, it will quench the triplets of the chromophore, and that will generate the singlet oxygen. Okay, so it will permanently deactivate the chromophore. But we found out that the chromophore didn't get permanently degraded actually. So from that point of view, we thought of the fact that okay, oxygen may not be entering deep into the chromophore region, because this surfactant liquid and the chromophore, they are in very low concentration actually. So they would be confined in the nano domains, not even in the micro domains actually.
Okay.
Yeah.
Okay, thank you very much.